Hi everybody, in this video we'll cover section 9.3 that's called Separable Differential Equations, and before we continue with expressing exactly what separable means, let's first discuss what is a differential equation, okay? So let's remember that calculus is the science of change, okay? And so far we've done rates of change, we've defined the derivative as instantaneous change of rate and so on and so on. But the real life problems involves way more difficult relationships between the functions and their derivatives, the second derivative, the first derivative, the second derivative, and so on and so on. So those are, as we're going to see, these kind of situations are modeled using differential equation. Okay, so before we continue, let's define what a differential equation is. A differential equation is an equation involving an unknown function y is equal to f of x and one or more of its derivatives. Okay? A solution to this differential equation is going to be a function y is equal to f of x that satisfies the differential equation when f and its derivatives are substituted in the equation. Okay? So one more time, a differential equation is an equation involving an unknown function y is equal to f of x and one or more of its derivatives. A solution to this differential equation, or a solution of a differential equation, is a function. So the function is the unknown, right? It's a function that satisfies the differential equation when f and its derivatives are substituted into the equation. So what would be examples of differential equations? Well, the easiest differential equation is y prime is equal to 2x, right? Very, very simple differential equation that asks you find y such that y prime is 2x, and this is very simple. Y is equal to x squared plus any constant, right? Don't forget the constant, because the constant can be 0, so y is equal to x squared, but the constant also can be 5 or any other constant, because y is equal to x squared plus 5 also satisfies this differential equation. You see, you're looking for y. How much is y such that, and then the differential equation is listed here. Okay. Now, differential equations of this type are very simple, and we've spent quite a lot of time in Cal 1 and Cal 2 doing them. When we talk about differential equations, we think of something more than this, where the derivative and the function itself play a role into this equation. Okay? So you see, it's not only y prime is equal to this term, but y prime plus 3y. So the question is, can you find y such that when you're going to put y into this equation, this is going to get the solution? The derivative also doesn't have to be just the first derivative. The equation can be y double prime minus 3y plus 2y minus 3y prime plus 2y is equal to 24 e to power of negative 2x. Again, the question is, find y such that the second derivative minus 3 times the first derivative plus 2 times y is equal to 24 e to power negative 2x. Okay? So for example, here, example number 2, verify that y is equal to e to power negative 3x plus 2x plus 3 is a solution to the differential equation y prime plus 3y is equal to 6x plus 11. And we have done problems like this in Cal 1, okay? What do we have to do? We have to find y prime, that's negative 3 e to power negative 3x, so I'm finding the derivative of y plus 2. And now, once I have y prime, I have y, let us plug this into the differential equation and check whether it's satisfied. So y prime is negative 3 e to power negative 3x plus 2 plus 3 times y e to power negative 3x plus 2x plus 3 is equal to 6x plus 11. Drop the parentheses on the left hand side. 3 e to power negative 3x plus 2 plus 3 e to power negative 3x plus 6x plus 9 is equal to 6x plus 11. Cancel the terms that you can cancel, and indeed the equation is satisfied. 6x plus 11 is equal to 6x plus 11. Okay, once we have covered what differential equations are, and as I said, we've done this in Cal 1, this kind of introduction, we can now start talking about a very, very simple type of differential equation called separable differential equation. Okay, so let's define what that is. A separable differential equation is an equation that can be written in the form y prime is equal to f of x times g of y. So a separable differential equation is an equation that can be written in the form y prime is equal to f of x times g of y. So let's spend 1 minute here talking about what this form means, okay? It means that we call a separable differential equation an equation such that on one side of the equation you have dy dx, and on the other side of the equation you have a product of two functions, of two expressions, one of them solely expressed, solely defined in terms of x, and the other one solely, exclusively defined in terms of y. Okay? So, for example, here I'm just going to list few examples of differential equations. Y prime is equal to x squared minus x plus 7 times y cubed plus sine of y. Okay, so this is f of x, this is g of y. You see, this factor is solely in terms of x, this factor here is solely defined in terms of y. Another example, y prime is equal to tangent of x plus 6x. Okay, here this is f of x, and g of y is simply equal to 1. Another differential equation, y prime is equal to secant of y plus y squared. Now here this is g of y, and f of x is equal to 1. Or D, usually separable differential equations are given like this: xy minus 3x plus 3x minus 2y minus 6. What do I want to say by this example is that the separable differential equations are not, don't have to be given in this form right away, okay? Sometimes they're asked in a question in a form like this, and it's up to you to bring them in a form like this, as a product of two functions, one of them defined in terms of x and one of them defined in terms of y. What does that mean? Well, for this particular example, for the first two terms I can factor x and I get 3 plus y. For the second two terms I can factor negative 2, and then in parentheses f y plus 3. And then finally the common factor, y prime here, the common factor is y plus 3. I factor that one out and I have x minus 2. And obviously this is indeed a separable differential equation. Sorry about that. Because it can be expressed, the change of y with respect to x can be expressed as a product of two functions, one of them defined in terms of x and the other one solely defined in terms of y. Okay? Now that we know what separable differential equations are, let's see how to solve them. Okay, so the idea here is that if you have y prime is equal to f of x times g of y prime can be expressed as dy dx is equal to f of x g of y. Okay, then you want to bring this in the following form. This is going to be 1 over g of y dy is equal to f of x dx, right? In a way, although we cannot treat this as a any normal ratio, but for this purpose here, we can in a way divide both sides by g and multiply dx. Once we're here, I have a function times the differential in terms of y and the function in terms of x times the differential dx. Then I can find integrals on both sides, and there you go. Here you're going to find a function in terms of y, and here you're going to find a function in terms of x. Okay, so let's start with the first example. Solve the following differential equation: y prime is equal to x squared minus 4 times 3y plus 1. Okay, first of all, we notice that this is indeed a separable differential equation. It's already factored, so dy dx is equal to x squared minus 4 times 3y plus 1. So the first important step here is to get to here. So we're here to get to here, sorry. Okay, so multiply both sides by dx, you have x squared minus 4 dx, and on this side you have 1 over 3y plus 1 dy. Okay, now when the left hand side and the right hand side are solely in terms of x, we can find the integrals. 1 over 3y plus 1 dy is equal to the integral of x squared minus 4 dx. Right, this integral is very simple. That's 1/3 x cubed minus 4x plus c. and the integral in this term is ln of 3y plus 1 in absolute value, right, times 1/3. Okay, the first question that somebody might have is, why here, when I'm finding the indefinite integral of the left-hand side, I don't have a constant? Well, you might, that's not necessarily true, because you can write here plus c or plus k, any other constant. We're going to bring that constant on this side. Constant plus this constant is just another constant, okay? So from now on, in order to save time, we're just going to add the constant when we integrate in terms of x. Okay. Now you have to find how much is y, right? You have to find an expression for y. Okay, so let's multiply here by 3 on both sides. And we get ln of 3y plus 1 is equal to x cubed minus 12x plus 3c. Now again, 3c is just another constant, so for this, at this moment I can call this one c1, right? Constant c1. Okay, so what do we have done from here to here? I've just multiplied both sides by 3. Now in order to get rid of the ln function, okay, I'm going to raise both sides. I'm going to bring e to power ln of 3y plus 1 is equal to e to power x cubed minus 12x plus c1. The left hand side simplifies to absolute value of 3y plus 1. The right hand side is e to power c1 times e to power x cubed minus 12x, right? Remember that e to power a plus b is equal to e to power a, e to power b, right? But again, e to power c1 is another constant, right? Let's call it c2. So here I have absolute value of 3y plus 1 is equal to c2 e to power x cubed minus 12x. Now we drop the absolute value. So dropping the absolute value of, let's say, h is plus or minus h, right? So you get plus or minus 3y plus 1 is equal to c2 e to power x cubed minus 12x. Again, I'm repeating, where are we going with this? We want to find how much is y. So I want to find an expression for y only. 3y plus 1 is equal to plus or minus c2 e to power x cubed minus 12x. And this is a linear equation. Here it's very simple to express how much y is. 3y is equal to -1 plus or minus c2 e to power x cubed minus 12x. Finally, y is equal to -1 plus or minus c2 e to power x cubed minus 12x over 3. Okay, so this equation here, if you find the derivative, okay, and you plug it in here, the derivative, and here you plug the function, this equality sign will be satisfied. Another thing that I want to mention is that this c2 is just a dummy variable for a constant. So do you have to write that 2 here as a subscript? No, not really. Okay, let's do another example. Square root of x squared plus 4 dy dx is equal to x e to the power 4 minus y. Okay, so let us look at this differential equation. I have a function, an expression in terms of x on the left hand side times dy dx, and here I have a function in terms of x times a function in terms of y. Okay, so let's see how are we going to deal with that. So first of all, I want to get to that expression where dy over dx is equal to a product of a function in terms of x and a function in terms of y, which means I divide by this term right here. So x over square root of x squared plus 4 times e to power 4 minus y. Okay, so this is f of x. This is g of y. Okay, that means that 1 over e to the power of 4 minus y dy is equal to x over square root of x squared plus 4 dx. Okay, this is nothing else but e to power negative 4 minus y dy, or the same thing can be written as e to power y minus 4 dy is equal to x over square root of x squared plus 4 dx. Now both the left hand side is expressed only in terms of y and the right hand side is expressed only in terms of x. I can proceed by taking integrals. So integral of e to power y minus 4 dy is equal to the integral of x over square root of x squared plus 4 dx. Here, if you cannot see what this antiderivative is going to be right away, you can use the substitution rule. X squared plus 4 is equal to u, 2x dx is equal to du, x dx is 1/2 du, right? So that means that this integral becomes 1/2 integral of 1 over square root of u du, which is 1/2 integral of u to power negative 1/2 du, which is 1/2 u to power 1/2 over 1/2. Cancel these two. So if you remember that u is x squared plus 4, so what do we have? Here we have x squared plus 4 to the power 1/2 plus c, and on the left hand side the integral of e to power y minus 4, the exponent is linear, so here you just have e to power y minus 4. Okay, now the only thing that you have to do is express this in terms of y. Take ln on both sides. Okay, ln of e to power y minus 4 is simply y minus 4 is equal to ln of square root of x squared plus 4 plus c. Finally, y is equal to 4 plus ln of square root of x squared plus 4 plus c. In the second part of this lecture, we will talk about boundary conditions, or in other words, how to evaluate this constant c here, and we'll do 3 more examples of separable differential equation. Thank you very much.